Hi, and welcome to the course Financial Mathematics for Actuaries. We are learning the loan repayment methods. In this session, we are going to learn how to compute the loan outstanding balances using the prospective methods and retrospective method, and also we will be developing one loan amortization schedule using the mathematical notations. So, as we have already said, that the loan outstanding balances can be computed using either the prospective method, which is basically the forward looking method. It calculates the loan balances at the present value of all future payments. On the other hand, we can also compute the loan balance using the retrospective method, which is a method that will be backward looking. It calculates the loan balances as the accumulated value of the loan at the time of evaluation minus the accumulated value of all installment paid up to the time of evaluations. Let us first uh, look at the prospective method. For this, let us denote the loan amount BL and the rate of interest per payment period BI. This loan amount L can also be considered as B0, or we can say like outstanding balance 0. Sometime you will find OB0. The rate of interest for payment period BIE, and the number of installment of an annuity is N. Then we can compute the installment amount A as using the formula A is equal to L upon A angle N at I, where this A angle N at I is nothing but your present value interest factor for annuity given N year and or N time and I interest rate, which can also be computed as 1 minus 1 plus I to the power minus N divided by I. Okay, to simple way we can take this as 1 minus 1 upon 1 plus I to the power N divided by I. This is nothing but your V to the power N, right? So it can also be computed as 1 minus V to the power N divided by I, where V to the power N is equal to 1 upon 1 plus I to the power N. Okay, or therefore we can write the A angle N at I is equal to 1 minus V to the power N upon I. Also, let us denote L is equal to B0, as I have already mentioned, loan balance at time T0. Immediately after the mth payment has been made, that is m is less than n, the loan is redeemable by a n minus m annuity. And suppose we denote the mth installment and we compute the loan outstanding balances at the period of m, that is bm. So bm is the loan outstanding balances at mth period, or we can simply have like this is nothing but your outstanding balances at m period of time. That can be computed as a time a angle n minus m at I. Okay, and we have seen that a is equal to L upon a angle at n at I. So using this formula, okay, using equation 1, which is A is equal to L upon A angle N at I. Using this, we can see that here we can rewrite this for A here L, this one, and then rest are same. So this is important for us. Okay. So using the prospective method, the loan outstanding balances can be computed as the installment amount A times the present value interest factor for annuity given N minus M time and interest rate I. Let us now look at the retrospective method. In the retrospective method, we first calculate the accumulated loan amount at time M, which is nothing but your L time 1 plus I to the power M, and also you will compute the value of installment, that is A time S angle M at I. This is the future value of interest rate factor for annuity. Okay, so you know that S angle M at I is the future value. This is future value interest factor for annuity given M and I rate. Okay, this one, which can be computed as 1 plus, okay, which can be computed as 1 plus I to the power M minus 1 divided by I. This is the formula we have used here. Okay. Thus, the loan balance can be written as this one minus this one. So, L time 1 plus I to the power M minus A time S angle M at I. Now, we will replace this value of L here and rewrite this equation number 3, and we will see that the retrospective method will exactly yield the same prospective method. So, to do that, rewrite the equation 3 again, that is L time 1 plus I to the power M minus A time S angle M at I, and putting this value of A here, putting the value of L as this. So, A time A angle N at I, and then rewrite the same thing again here. This is simply this one, and this is simply this one. Okay, we then take this A out and put the value of A angle N at I here as this one. This one, the value of this is nothing but your A angle N at I. So you'll have, we can write it as A time 1 minus V to the power N divided by I multiplied by 1 plus I to the power M minus, okay, this one 1 plus I to the power M minus 1 divided by I, the formula what I have just written earlier. Okay, now, so note that this one can be simply written as V to the power minus M. Okay, so this can be this one, this value, it can be written as V to the power minus M, and therefore we can we can solve this, or we can simplify this to A time 1 minus V to the power N minus M. Okay. So this can therefore written as A time A angle N minus M at I. This formula what we have already seen in the prospective method. So what we have seen here is both prospective method and the retrospective method yield the same answer. Now let us look at the loan amortization schedule. To do this, let us apply the prospective method. Here, suppose that a loan is to be repaid by an N payment unit annuity. Unit we will come that 1. Okay. So the installment amount will become 1. Okay. The initial balance, that is B0, sometime we will write as the outstanding balance OB0, which is equal to L, is also equal to A. This one, this can also be A angle N at I, which is this one. Okay, A is written here, A is 1, so you can just mention it here. Okay, so the interest incurred in the first payment period is I time this one, which will be I time A N at I, which will become 1 minus V to the power N. Okay, we know that this interest or the present value of interest factor for annuity given n time and I interest rate is nothing but your 1 minus 1 upon 1 plus I to the power n divided by I. Thus, out of the unit payment, 1 minus v to the power n is going towards the interest payment and the principal is reduced by v to the power n, and the principal would be A angle n at I minus v to the power n, which will become equal to 1 minus v to the power n divided by I minus v to the power n. So, taking the LCM, we will get 1 minus v to the power n minus I time v to the power n divided by I. Okay. And now take this v to the power n out, we will have 1 minus v to the power n multiplied by 1 plus I divided by I. Now we can rewrite this as your v to the power minus 1, that is I have written it here. So 1 minus v to the power n multiplied by v to the power minus 1 whole divided by 1, and then we can rewrite this as v to the power n and v to the power minus n, then we can have v to the power n minus 1. So I will have 1 minus v to the power n minus 1 divided by I. Now considering this as 1 part, that is, let us say it will become x, then we will have 1 minus v to the power x divided by I. Okay, or we can write this as like this will become A angle x at I. Okay, same way we have written it here, right? That is A angle n minus 1 at I. So, this is the way we can compute the loan outstanding balances using the prospective method in the loan amortization schedule. So, using this, now you can develop the generic loan amortization schedule, which will look like this. Okay, here let us understand this one by one. Notice that this one is your loan outstanding balances or initial balances, which can also be seen as L, or sometime we will see that B0 or outstanding B0, whatever way we can call it, but we understand that this is simply A angle n given the I is understood, so I is not written here, but you can read it as A angle n at I. Okay, and the installment amount is the 1 because we had unit installment. Okay, and the interest payment is I time this one, this is this I time A angle n at I, which will become 1 minus v to the power n, or this is the principal reduction. This is simply we have here like this one can be, sometime you will find in some book that it will be K1, or if it is a level payment. So level payment in the first period, it is K1, which will be equal to 1 in this case. Okay, and therefore we can simply have this one. This is principal reduction, which will be K1 minus this. This is also called like interest payment. So we can simply have, we can make it like I1. So K1 minus I1 will give you this one. This is V to the power n. So here we will have K1 minus I1. This is the way we can also understand the principal balance. So whole point here is, first we need to compute the interest payment, that is the stated interest rate. Okay, interest rate times this one, that is I multiplied by the initial loan balance, which will give you 1 minus V to the power n, and then we will subtract this value from the installment you have paid, which will be the value that will be go towards the principal payment, that is V to the power n, and then the outstanding balances therefore will become the outstanding balance at this period minus this. So this one, that is B0 minus this one. This is the principal reduction here. So the principal reduction here, principal reduction 1, we can simply have, okay, or we can write A angle n at I minus V to the power n, which will be equal to, this is what we have already computed in the previous slide, right? So like this, if you will go on for t period of time, we will get the value here. The total amount that will go towards the principal payment is equal to 1 minus V to the power n minus t plus 1, and the total amount that will go towards the principal reduction will be simply V to the power n minus t plus 1, and the outstanding loan balances at the t period is equal to A angle n minus t at I. Similarly, we will go on to the nth time period, and we will find that the total amount that will go towards the interest payment will become 1 minus V, and the total amount that will go towards the principal reduction will become V, and the total outstanding balances will be reduced to 0, and therefore the total interest payment you have made is n minus A angle n, and the total amount that is just equivalent with this one is the equivalent with the initial loan balances. Okay, so graphically you can see this as, initially the interest amount will be high, and then as you proceed, okay, till the nth period, the interest amount or the amount that will go toward the interest rate is gradually decrease. Okay, however, the amount that will go toward the principal reduction will gradually increase. So if you put it in a graph, then you can see the graph look like this. This is theoretically, the graph is drawn here. In x-axis I have measured time, and the y-axis I have measured the payment distribution, and you can see here that initially, okay, this is the amount that will go to, initially the amount will be high, but gradually it will decrease over the time till the loan. On the same time, the amount initially that will go toward the principal reduction is less, but gradually the amount that will go towards the principal reduction will be increased, and therefore in the last period your loan balance will become 0. So this is how the loan amortization principle work. Now in the next session we are going to take some of the numerical example to compute the loan outstanding balances and the loan installments, and also the amount that will go towards the loan principal reduction and the amount that will go toward the interest due. Okay, and also we will construct the loan amortization principle using the Excel. Thank you.